Let's start with what it means for a sequence to converge. A sequence converges to a limit, capital L, if for every small tolerance you pick, the terms of the sequence eventually get and stay within that tolerance of L, forever after some point. If no such number exists, the sequence diverges. The good news is that the limit laws you already know from functions carry over directly to sequences, so limits of sums, products, and quotients of sequences behave exactly the way they did before, term by term. Next, the monotonic sequence theorem. This says that if a sequence is always increasing or always decreasing and it is also bounded, then it is guaranteed to converge. Notice this needs two conditions together, monotonic and bounded. There is also the Squeeze theorem for sequences. If a sequence is trapped between two other sequences, both of which converge to the same limit, then the trapped sequence must also converge to that same limit. Now let's work through an example. We want to determine whether the sequence open bracket 2m plus 1 close bracket divided by open bracket n plus 3 close bracket converges, and if so, find its limit. Step 1. Divide the numerator and the denominator by n. This gives us the quantity 2 plus 1 divided by n, all divided by the quantity 1 plus 3 divided by n. Step 2. Take the limit as n approaches infinity. The terms 1 divided by n and 3 divided by n both shrink towards 0, so the numerator approaches 2 and the denominator approaches 1. Step 3. Apply the quotient limit law. The limit equals 2 divided by 1, which equals 2, so the sequence does converge, and its limit is 2. Here is a useful trick for checking monotonicity quickly. Instead of setting up a full derivative-based argument, just compute the difference between consecutive terms a sub n plus 1 minus a sub n and check its sign. Or, for sequences of positive terms, you can instead look at the ratio a sub n plus 1 divided by a sub n and check whether that ratio is always greater than 1 or always less than 1. Now, a common trip-up. Learners often assume that being bounded is enough on its own to guarantee convergence. It is not. A sequence can be perfectly bounded and still oscillate back and forth forever, for example, alternating between two fixed values like -1 and 1. That sequence never settles down to a single limit, so it does not converge even though it is bounded. So here's a teaching tip to take away. Always treat monotonic and bounded as two separate checkboxes. Before you use the monotonic sequence theorem to conclude convergence, verify both conditions explicitly, in writing, every single time. Never assume that satisfying one of them automatically means the other one is satisfied too.